This is video number 2 for waves. So amplitude, now if you have a wave created by that person again with a slinky, there's a mean position for the slinky, which where it would be if it was lying flat. The amplitude, so mean position, height from the mean position to the crest, or it could be the height to the trough. Okay, so that is the amplitude. So we've got the mean position, the average position, the rest position. The amplitude is the height to the top. Okay, it's measured in meters because it is a height. Symbol A, unit, meters. Wavelength is a distance from 2 points on the wave that are doing the same thing. Okay, so we can say that that point to that point are doing the same thing. They've just been rising up and they're about to come down. Rising up and about to come down. So those two can show the wavelength. It could also be from there to there, is on the way down. It could be from there to the next trough. It could be from there to there. Okay, so the wavelength is from 2 points doing the same thing, the distance between them. So symbol is wavelength is lambda. And the unit is meters. It's a distance measurement. Period. Okay, the period is the time for one oscillation. Okay, so if you had your stopwatch and I had a wave, so if I go up like this and I go down and then back to there, you could say, oh hang on, I'm going to try that again. So let's say we're starting from the middle here. We go from there back to there. That's one oscillation, and the time it took will be the period. Okay, so on this graph here we've got now time on the x-axis. Before we had distance, now we've got time. It is the time to go for one complete wave. Symbol, capital T. Unit, seconds. Frequency is the number of wavelengths past a point in 1 second. So let's say imagine there's some waves being created, okay, and they're travelling along. So in the future, the crests and stuff will change, okay, they'll be moved along. Now, if you're standing at this line here with a stopwatch, and you time for 1 second, and you count how many full waves go past that point. So full wave is from there to there again, oops, from the middle to middle. That's 1, and then back to there, 2, and so on. So if both of these waves went past in 1 second, then it would have 2 Hertz. Okay, 2 waves in 1 second. So symbol F, unit is Hertz. So probably an easy way to show this. Could be a point, and you could have a wave, and then we'll just colour in part of the wave, and we could say we have time of 1 second, 2 waves, and that equals 2 Hertz, something like that. So 2 waves per second is 2 Hertz, or 2 full oscillations is 2 Hertz, and so on. But also, period is the time for one wave. Okay, so time for one wave, and frequency is the waves per one time. Okay, so they're actually inverses of each other. So frequency is 1 over the period, and period is also equal to 1. What am I doing? 1 over the frequency. So for example, if we had a period of 4 seconds, so that means we have 4 seconds for one wave, then the frequency is equal to frequency equals 1 over the period, so that's 1 over 4, so it equals 0.25 Hertz. And that makes sense. It takes 4 seconds just for one wave. So how many waves are there in 1 second? Well, there's a quarter of a wave. Speed is how fast the energy of the wave travels. Okay, symbol V, unit meters per second, just like before. Speed is V equals d over t, which we've seen before. But for a wave, the distance equivalent is lambda for distance, period for time. So the time for one wavelength, okay, is what we have here. So we're going to use V equals F lambda, or V equals lambda over t for velocity.